This is a review of Calculus AB student, December 2021, session slides for a Chapter 4 review for an exam. In this chapter, we're studying functions, mostly polynomial, but some trigonometric, with first and second derivative tests, constructions, and the related concepts of the mean value theorem and L'Hopital's rule. For question number 1, find the x-coordinate of each point at which S obtains the absolute maximum or absolute minimum value. For each coordinate you give, state whether it contains an absolute maximum or minimum. As you can see on the given table, only certain key values are shown for the function, so we plot those first. And then whether they're increasing or decreasing in each interval, we loosely draw the lines given the first derivative, and then for the concavity of the second derivative. Student was not familiar with the idea of up like a cup, down like a frown, or other mantras to learn the concavity shape of the curve, which would be plotted, I suppose, generations ago with, say, a French curve or other such architectural tool. But here a cusp is formed at 2, -1. The student was able to identify the concept of maximum and minimum when shown the picture on the right, and correctly identified 3 points so that the function had 2 minima and 1 maxima in the local domain of -3 to 3. For question number 2, refer to the graph and the information below. Here the graph of the derivative is given in this standard problem for a Calculus AB exam. And from those slopes, I blocked off the positive slopes, showing that the function must be increasing during unit 0 to 6. What's in the red box should be done directly below the graph, and the graph of the climbing function from 0 to 6 should be offset below, so the student can differentiate between the tracking the function in chunks, say of unit times, and that the behavior of the graph will be increasing across that green region. Once it reaches 6, it reaches a plateau, or local or absolute maximum at 6 units, and then the graph is decreasing, but at a much slower rate than it was increasing. Therefore, based on those facts, although point 8 is a local minimum, point 0 must be the lowest point, because we just spent 6 units climbing at a much higher slope rates of like 3 and 2 at points 1 and 3. So the graphic that was to aid this student should be offset with the graph here below that red bar of the lattice points of each slope. Okay, but that is a way to grasp when you're not given a function rule, but you're given a continuous graph of the first derivative to as an aid to reconstruct the original function. Also, the concept of the vertical shift or starting point was not known by the student. It was not taught by the teacher. So the student didn't understand that it could be anchored at any point, that the constant c of an integral, that concept was not discussed in class. So the integral or antiderivative was not part of the pedagogy of this teacher. Number 3, again, a derivative graph is given, and so we had to find the local extrema. I explain once again using chunks above and below the x-axis. When the function itself is below the x-axis, that means that the original function is decreasing, and then when since it doesn't matter where the function begins, we can just anchor it at 0. But we know that when it starts at point A, the function itself was decreasing to a minima. Then at the point circled with the first green oval, that is a change from decreasing to increasing, so it creates a local minima. The student was unaware of the concept that, well, we don't really get the shape of the increase, but you can see it's increasing fast, and then it reaches its maximum increase, and then it is decreasing. Once it reaches the second oval, that will be a local maximum. It will be changing from a first derivative that's positive to negative. Student was unaware that it's the change in sign of the first derivative that creates these local maxima and minima. That he said that was in the reading but was not discussed by the teacher. So for this tracked object, it will have 2 local minima and 1 maxima for this interval. On to question 4. Consider a differentiable function having domain f prime of x is 4 minus x times x to the negative 3 for x is greater than 0. Again, a very poor font choice by the College Board review book. The prime is barely seen in most of these examples, causing student confusion. So that is a textbook error. Student was unaware of the analysis line test for first and second derivatives. Said that was not discussed with his teacher. You draw a number line, find the critical points, and box them here. By rewriting x to the negative 3 in the denominator, it's easier to find the values when the denominator is 0. At 0, the function is undefined, and the numerator is 0 only at x equals positive 4. This creates 3 region intervals, but since we don't care about when, because x is restricted to greater than 0 in the text, right? We have a positive domain. We really just need a test point on the left side of 4 and on the right side of 4. Student was enlightened by this idea of, oh yeah, just any random point to the left or to the right of 4. And then the behavior of any continuous function, all the points on the left are positive, all the points on the right are negative. So this was a good organizational tool for the student. Again, this was given to me in high school when I took BC Calculus. By plugging in, realizing that the sign change of the first derivative means that the function itself went from an increasing to a decreasing function, means that at the point 4, when the derivative is 0, that is a local maximum. Student was further confused by this notion of positive to negative and negative to positive for question 4. So I gave as an example whatever the first thing came to mind. So you're traveling from Columbus to Cleveland. Well, if you were going uphill and then downhill, like over a mountain, that would be a local maximum. If you went down into a valley, walking downhill and then back uphill, because it's a critical point at mile 4, that would be a minimum. So you need to figure that out for your teacher based on the function rule for the first derivative. When I asked, do you have any integration techniques that use for the product of 2 functions? How do we integrate a function like this? The student was unaware of what I was referring to. So I said, well, the other way to do this is to take the integral of 4 minus x over x cubed. And I said, well, what integration techniques do you know? The student said, well, we haven't done that yet. So I said, well, then we're just using it as with this analysis line. And he said, what? And again, was unfamiliar with this organizational tool. For the next question, number 5, we didn't save the slide, but we were given a graph with the point 1, 0 on the graph, which had a positive slope at 1 and was concave down at the same point. So the correct answer was choice D for the graph picture that was given, with the point 1, 0 showing a positive slope but concave down. For question 6, here we're given another 5 points on the graph, A, B, C, D, E, and we want to know when the first derivative and second derivative are both negative, meaning that the slope is negative and slope of the tangent is negative, and it is concave down. And that only occurs at point B, like Bravo. Point D, let I'm sorry, point C has a negative slope, but it is concave up. So it was between B and C, but it was B for question 6. So you would test with the first derivative first, eliminate, here I colored positive slopes in green and negative slopes in red. So the function is increasing at A and E, but is decreasing only at B and C. So after going through that checkpoint, then go to the second derivative and check for concavity. And B was concave down. And here were my notes with like a little kiddish cup here on the right for the second derivative up like a cup. For question 7, here we're given a domain T between 2 and 4. And for the coffee maker, like a Mr. Coffee machine on the right that I drew with the cone drip coffee, you can see that the rate of dripping is decreasing between the intervals by doing the difference graph as an approximation for C prime of T. So this shows that during the first minute, when most of the fluid is in the cone, the weight of the fluid is dripping the coffee out at 5.3 ounces per minute. But by the second minute, because there's less weight in the cone of the actual liquid, the drip rate is slowing down. So although this is continuous, we can approximate it with these minute intervals. And since we know that the drip rate was 2.4 ounces per minute at in between 2 and 3 minutes, and 1.6 in between 3 and 4, it's that block of time that is the time between 2 and 4. So somewhere the rate change was 2 because it's a continuous function. So since it was dripping at 2.4 ounces and then became 1.6, somewhere in that time frame, the drip rate was exactly 2 ounces per minute. So the student understood this concept of the rate of change slowing down, for example, in a coffee machine, and was able to visualize it as well. Here I drew it as a tiered bandwidth, showing that more coffee in the first minute and then pour the amount on the second minute, and how these strata, like a log graph, the bands are getting smaller because the drip rate is decreasing in a continuous rate. Okay, so although the function that governs this process might not be a logarithm, might be an exponential or another trigonometric model, it gives the student the idea of the decreasing slope, right? The decreasing amount of coffee for each minute of this minute 0 to 6. Question number 8, what intervals is any interval is the graph both decreasing and concave up? So again, I had to redraw analysis lines because the student hadn't done this for first and second derivative. And then for this, I said, well, what model would we use for the function given? F of x is x minus 3 times e to the x. And the student said, well, let's use a chain rule. I said, well, it's not a composition. It's like function A times function B. So we can't use the chain rule. So I put down the 3 basic templates for product rule, quotient rule, and chain rule. And certainly the student finally got, after about 5 minutes, that we should use the product rule. The derivative of e to the x is e to the x, which creates very elegant elements here. So the first derivative, although the original function was x minus 3 times e to the x, the first derivative is just x minus 2 times e to the x, meaning that the first derivative is the exact same curve shape with the vertical shift lifted 1 unit with the first element. So although the graph itself doesn't look like a vertical shift, the first element was given a vertical shift of 1 unit of the product of the function A. So with that in mind, we looked at the critical points, and since e to the x is always positive, we just have to find the zero product based on the first factor. So it's 3 with the first derivative, but it shifts to 2 with the second derivative, meaning that there is an interval, that gap between 2 and 3, where function f is, yes, it's decreasing, but it's cupped up. Right? And so then I drew the local picture down below. The student understood the idea of the analysis line, and like inequalities of the overlap of both conditions creates an interval and not two opposing rays. So that was question number 8. So again, the use of this metric, the test line should be templated by any calculus student, because it really helped with understanding. And then by doing this quick sketch at the end of the local picture, well, what's happening between 2 and 3, oh yeah, it's decreasing in concave down. And then once it reaches 2, it flips to concave up for the rest of the function. But it doesn't, although it's concave up, the function itself is still decreasing up until 0.3, when then it's concave up and increasing. So student understood that after looking at the two analysis lines. Question number 10. What are the values of x for the function f is defined by? F of x is this cubic polynomial. So for the first derivative, the student was able to independently do the first derivative. And then when we found the critical points, he was like, well, why do we do this? I said, well, you're going to do the analysis line by yourself. I said, well, how do you do that? So set it equal to 0, factor it. And the student was able to do that by scaling, actually scaled it himself, divided everything by 3, and then factored it, but had the incorrect factor, so we corrected that. When we went to the analysis line, you can see that the critical points are -3 and 1. So the student didn't understand that, well, now the infinite number line is divided into 3 sections. So we needed test points like -5, 0, and 2. So that means x is less than -3 or x is greater than 1. And plugging in, I said what was important was just the signage, and to use the factored form of the trinomial, since you already did that work, it makes the math work faster. So you can see that the region on the left is positive or increasing. The region between -3 and 1 is negative and then positive. So where was it increasing? The correct answer is C. When x is in a region less than -3 or when x is greater than 1. For the next question, number 11, a limit of e to the x minus cosine x minus 2x over x squared minus 2x. So by plugging in the limit value, we get a 0 or 0 situation, which means that this problem has passed the checkpoint for L'Hopital's rule. So we know that when we plug in, or if we get a 0, 0 or infinity over infinity situation, that we can take the first derivative of the top and the bottom. So if both rates are approaching 0 or infinity, we can take the derivative and compare that ratio as well. So then we had e to the x minus sine x minus 2 over 2x minus 2. So now the 2x, which was a polynomial term, becomes a 2, which was what was needed, usually just one iteration when you have a linear terms like that. So then we have 1 minus 0 minus 2 is -1 over 0 minus 2, and we get that the limit is a half. The correct answer was C. So that's a one iteration of L'Hopital's rule. For question number 12, we're given the prime functions, cosine x and g of x, cosine and 1. But we're given that the original functions, whatever they may be, so I guess negative sine x and like it could be x plus 9, x plus a constant, that the limit as it approaches 0 is 0. So it must be, the constant must be 0, like x plus 0 for the linear function, because it has to approach 0. So the two functions are therefore negative sine x and g of x must be x. But at any rate, since we're told already that we have a 0 over 0 situation for the limit, we're permitted to stack the derivatives. Cosine x over 1. When we plug in 0 into those functions, we get 1 over 1, which is 1. So that means the limit of the original functions, the ratio of the functions f of x over g of x, is also 1. So that means the limit of sine x over x is negative sine x over x is 1, for example. Okay. I'm sorry, the derivative of sine x is cosine x. The derivative of sine x over x is 1. Okay, so that was using L'Hopital's rule for that unusual ratio function. The student was unaware that cosine began at 1, so by drawing the graph, the student immediately remembered that visual aid. So perhaps prepping 3 slides with the cosine, sine, and tangent functions as an aid that can be pulled, the file can be pulled up and put on screen immediately, would save a few minutes of tutoring time. Question number 13. A particle moves along the x-axis, so its acceleration at any time t is a of t is 2t minus 7 if the initial velocity of the particle is 6. At what time t during the interval 0 to 4 is the particle farthest to the right? Well, what do you see here? Well, I wanted to connect to hard science physics, so given the acceleration, I said that, well, that's the second derivative of the original position graph. So I said, well, that's the antiderivative would be the velocity, and the antiderivative would be the distance. The student was unaware of this relationship, did not have it organized. When I said, well, let's piece back together the velocity function as well as the position function, the student was unaware of how to do integrals. And I said, but didn't your teacher do the unit on integrals? Said, yes, but not really. I said, well, what does that mean? I said, well, can you do it backwards? Because it's a two-way street. You can do derivatives using the power rule, but you can also do it in reverse. That's called an integral or antiderivative. Student said, yes, I'm aware of that, but was unable to do it term by term. So I assisted and drew the pink graph term by term with the constant c, which the student was unaware what the c represented. At any rate, we can solve this with the first analysis test because we want to know when the particle is furthest to the right. And based on the behavior of the velocity between points 0 and 1 times 0 and 1, the particle had a positive velocity up until point 0. But then after time 1 between t equals 1 up to 4, during that entire time, the particle had a negative velocity, meaning it's moving to the left. So since it swings to the right and then at 1 second is moving to the left for the rest of the time interval up to 4, at t equals 1 must be the critical point where it's farthest to the right when being tracked. So the student understood this idea based on the analysis line, that the critical point, and then when we drew it, that since it's traveling along the x-axis, it's just traveling back and forth with third interval time, understood the idea of tracking, that the particle would be tracked. We would see it as going back in the other direction from units 1 to 4. Another limit problem, the student was able to do L'Hopital's rule after figuring it was an indeterminate form 0 over 0 once again, and correctly stated that it would be a half. For question number 15, the student said, yeah, I did this with my teacher. Yeah, we did this before. And I said, well, what's the answer? The student immediately said, well, it's negative a half. And I said, well, how do you get that? And he goes, no, I just know it. So I realized that he was holding the answer key in his hand and it was tired. It was already after midnight. So this is an interesting problem because it shows that the square term is what becomes constants first after 2 iterations of L'Hopital's rule. This is a good student example because it shows you have to do L'Hopital's rule twice, and then the coefficients become positive 16 over negative 32, which is the correct answer A. So this is, you have to do L'Hopital's rule twice after this is 0 over 0 indeterminate form. Last one, number 16, we're given the function on the top right, which I've highlighted in green and red. So that was the drawing. It looked like a standard cubic, right, with just 2 turns and the rest in a continuous function. The student incorrectly chose D, that it looks like, oh yeah, it looks like it's increasing, so it's positive, and then it's negative during the red block, and then it's positive again. Because, and I said, well, that's true, but those flares at the end, see how it looks like antlers or like a bull's head? There's no change, there's no twist, there's no concavity. So there's no change in concavity. So D is a trick answer. E, the parabola, is actually correct, right? Just like if you have a cubic, like ax cubed plus bx squared plus cx plus d, the first derivative is a parabola. So it's not that has 3 terms. That would be a 4th degree equation minimum, right? So D is the trick answer. That's a quartic, at least a quartic, and E is the correct answer as a parabola. The student understood that. He could see that, oh yeah, the original function, that there are no other twists or turns or inflection points. But it was late, and we ended on this question, number 16. So this was an example of a long tutoring session for a student getting ready for a unit exam. And again, the tools that are used here are just a Zoom animator. Nothing is preset. It's all done in real time. But again, the student was not familiar with these visualization methods of when given the function or first derivative of chunking during the positive and negative regions, or a positive slope and a negative slope, like highlighting them in red and green. The student was also not given the method of an analysis line for the first derivative and second derivative tests, which makes no sense to me because that's primarily what the lesson is doing when you're focusing on a single derivative and the critical points. So, and then test points in a region, the student was unaware of that from any teaching pedagogy. And finally, the idea of the integral, although the student said, yeah, that's going to be on the exam, the student, although could do the power rule and the product rule based on rote memorization, there was no lesson that seemed to have been given on integration of polynomials term by term. So it was not able to reconstruct or understand the idea of the C constant, so vertical shift, that doesn't change the first or second derivative, because when you take the derivative of a constant, it becomes zero term. So the idea of a vertical shift was not discussed by his teacher. So again, this is Calculus AB tutoring during COVID. Thank you for following and watching this interesting video from this tutor. Take care. Bye.